So, the truncation error arise when we have a we can write a very short form truncation error. So, in short we have written the error due to truncation of an infinite series to a finite number of terms. And we define the order of truncation error. Order of T is the least power of or least order of lowest power of H or least order of H or lowest power of H, because this is a series in a power series of H, the steps H. So, this becomes the lowest order or lowest power of H. So, now this formula gives us the way the derivatives can be approximated. Now, let us substitute the approximation to the given boundary value problem. So, we have the boundary value problem. If we recall, y double dash plus a x y dash plus b x y at equal to c x. So, at x equal to a grid point, any grid point x I, we have y I double dash plus a I y I dash plus b I y I equal to c I, where we denote a x I equal to a I and so on. Now, replacing the or approximating, I think that will be the better term. Approximating only the better term. Approximating the derivatives by finite differences, by central differences. We get, if I now approximate the derivative by central difference formula, so here we y I plus 1 minus twice y I plus y I minus 1 by h s square plus a I y I plus 1 minus y I minus 1 by 2 h plus b I y I equal to c I. So, this is the one is called the discretized equation, which is referred as the TIS discretized equation. Now, at each grid point, so this for I equal to 1 to n minus 1. Now, we are looking for the values of y0, y0 yn is given. So, y1 to yn minus 1. So, if I put together collect the like coefficients and put in this manner, yi minus 1 plus bi yi plus ci yi plus 1 equal to di for I equal to 1 to n minus 1, which forms a n minus 1 linear, these are linear algebraic equations involving n minus 1 unknowns. What are the n minus 1 unknowns? Are y1, y2, yn minus 1. Because y0, yn are appearing, but they have given values are prescribed, so that can be transferred to the right side. So, say for example, if I put I equal to 1, so which looks like a b1 y1 plus c1 y2 equal to d1 minus a1 y0, which is given. The next is, this is for I equal to 1, I equal to 2 if I substitute, so I get a2 y1 plus b2 y2 plus c2 y3 equal to d2, and so on. I equal to last one is given a n minus 1 y n minus 2 plus b n minus 1 y n minus 1 equal to d n minus 1 minus, because this is known, so this is yn. We can transfer to the right side, the known side. So these are the system of linear algebraic equations. So right side is the known vector. Now if I put in a matrix form, so writing, let us call this is the system of equation as 1. So if I now introduce a vector, let x transpose is this vector y1, y2, y n minus 1, vector of unknowns. So star can be the system 1, not star, 1 can be expressed in a matrix equation. As Ax equal to, let us call Ax equal to B or capital T, where A, how it looks like, A or this matrix, say if I write the first row, it will be B1 C1, all the elements are 0. Next row A2 B2 C2, all the remaining elements are 0, and like this way, and any ith row, what you find that these are all 0, and except A, I, AI, BI, CI, and okay, so let us call these are the zeros. So these are all 0 elements, and finally the last row will be a n minus 1, 2 elements, a n minus 1, b n minus 1, and here it is multiplied with the vector y1, y2, y n minus 1 equal to this is d1 minus a1 y0 and minus a1 y0 d2 and dn minus 1 minus cn minus 1 yn. Okay. So the matrix equation looks like this form. So this kind of matrix A is called a tridiagonal matrix. So solution will be basically what we are looking for, the solution x equal to A inverse t. So now our task is to solve this, to solve the tridiagonal system. tridiagonal system. Now, if the matrix is a tridiagonal, so it is very little easier compared to other situation, because a tridiagonal matrix can be very easily converted to a lower triangular matrix or upper triangular matrix. So, before that, let us consider a simple situation. Consider this linear boundary value problem. Say x square y double dash plus xy dash equal to 1, y1 equal to 0, y at 1.4 equal to 0.0566. So, if I choose h equal to 0.1 and xi equal to 0.1 I will be 0, 1, 2, 3, 4. So, 0 and 4 are the boundaries. So, y0 is 0 and y4 is 0.0566. Now, if I discretize and write the boundary conditions and all, so what I find that this equation becomes 2.31 y0 minus 4.84 y1 plus 2.53 y2 equal to 0.02. So, in other words, I can write these as minus 4 or, because this is y0 is given to be 0. So, you can transfer to the other side 4.84 y1, 2.53 y2 equal to 0.02. This is equation 1. Now, our unknowns are, so these are given to get y1, y2, y3, 3 unknowns. So, this is the first equation. Next equation is 2.76 y1 minus 5.76 y2 plus 3 y3 equal to 0.02. This is equation number 2. Then next equation is 3.25 y1, 6.76 y2, y3, sorry, this is y2 and y3 equal to 0.02 minus 3. Because it will be y2, y3, y4. So, y4 is 3.51 into 0.0566. This is the y4. So, this is the constituting the equation third. So, we have now 3 linear algebraic equation which can be solved, and that looks like it will be the solution as 4, 6, y2 equal to y2 equal to 0.0167, y3 equal to 0.0345. Now, we are lucky because we have a 3 by 3 matrix equation or 3 by 3 system of equations, so which can be solved quite easily by this manner. But if we have a large number of system, so in that case we may not be that lucky to solve by a manual procedure. So, that required a algorithm which we will describe now. So, this is called the Thomas algorithm for tridiagonal system. Ax equal to say d. So, we have a tridiagonal, say A is a, in general let us call n by n tridiagonal matrix. Say this is B1, C1, 0 0 0 shown A2 B2 C2. So let us put a big 0 over here, and the last one AN BN, and this is a x1 x2 xn. This is the vector of unknown, and d1 d2 dn. So in this, what we will do is reduce A to a triangular matrix. Triangular matrix by elementary operations. So that means what I do is, before the diagonal elements, all the AI positions we bring 0, diagonal positions we bring 1, for example, and so the reduced form is 1 C1 dash 0 0 0 0 1 C2 dash, and the last one is 1, and this is 1. So this is x1 x2 xn. So obviously these coefficients also get changed because we are doing the elementary transformation. So the coefficients are altered. So now we get a triangular system where all the elements are 0 at the last one. So this is the 1, and the next one is all 0. So next one, if I write, this is Cn minus 1 dash 1, and this is all 0. So this is 0. Now once I have a system like this way, I can very easily write the solution as xn equal to dn dash, and xi equal to, if I go by back substitution, so di dash minus ci dash xi plus 1 for I equal to n minus 1, n minus 2, etc. 2, 1. So first one, I get the last last variable xn from the last equation, that is, we get the first, then subsequently last but 1, and so on. Now we need a algorithm. So what is ci dash and di dash are what? So if I know how to relate the ci dash and di dash with the given a1, b1, ai, bi, ci, di, etc., so then we are through. So at this stage we get the solutions which is required to be obtained. So Thomas algorithm, and also one can also derive, that is, if we do this step by step procedure. So where we write this way, where C1 dash equal to C1 by B1, I think it is very easy to say this one, and D1 dash equal to D1 by B1. We are just, first row we were having B1 C1, so we just divided by B1, and we get this, and Ci dash equal to Ci by Bi minus Ai C dash I minus 1, and Di dash equal to Di by same thing, Bi minus Ai C dash I minus 1. This is for I equal to 1, 2, 3, etc. up to n. So once, so the procedure is, so the procedure, discretize the linear BVP, get the tridiagonal system. That is AI, BI, CI and DIs. Then use Thomas algorithm to get CI dash DI dash by this manner, and then solution is xn or yn equal to dn dash and xi equal to di dash minus ci dash xi plus 1. So, I equal to n minus 1, n minus 2, 2, 1. So, this is the simple steps one need to follow to solve the linear boundary value problem. So, once I derive the discretized form and then the tridiagonal system, so one can determine the AI, BI, CI, DIs are determined. So, through that we compute the CI dash, DI dash. Once those are computed, then the solutions are obtained. So, one can solve this problem xy, y0 equal to y1 equal to 0. Let us take h equal to 0.25 and use Thomas algorithm to obtain the solution. So, solutions are so these are the solutions of the given system. So, that is how the tridiagonal system goes. Now, here one thing to be noted is that the order of accuracy, the truncation error, order h square, so h has to be quite small. So, this implies the n, the number of grid is quite large. So, that is to say the order of A is large. Now, because this tridiagonal structure of the matrix A, so we could get a algorithm, the Thomas algorithm, which is a direct algorithm without doing any iteration like Gauss-Seidel or Gauss-Jacobi's. So, one can obtain the solution directly. So, that is the advantage of having a tridiagonal system. Okay. Now, so this Thomas algorithm is a direct method, no iteration involved. But the given matrix should be tridiagonal. Now, one thing is that for getting a tridiagonality, you have to use 3 points. Now, if I go beyond 3 points, so that difficulty arises that we may not get a tridiagonality. Now, some of the boundary value problem in BVP, the boundary conditions can be in the derivative. Or prescribed as say alpha 1 y a plus alpha 2 yb equal to gamma, this is y dash a, this is one boundary condition, and say beta 1 yb plus beta 2 y dash b equal to gamma 2. So, this is the situation, then there is a difficulty. Now, I equal to 0 corresponds to x 0 equal to a. So, now if I were to approximate y dash 0, so in terms of that, so the boundary condition looks like alpha 1 y 0 plus alpha 2 y dash 0 equal to gamma 1. Now, if I want to use the central difference over here, so that means, but our grid starts from 0. So, this is 0, 1, etc., and that is n over n, last point. But the derivatives are involved at y dash 0. Similarly, beta 1 y n plus beta 2 y n dash equal to gamma 2. So, one remedy is to choose fictitious points, say this is minus 1 and this is n plus 1. So, if I introduce I equal to minus 1 and n plus 1 symmetrically, so in that case I can replace y dash 0 as y 1 minus y minus 1 by 2h and y n dash equal to y n plus 1 minus y n minus 1 by 2h. So, our grids are now I equal to minus 1, grids are 0, 1, etc., n plus 1. So, we have the how many grid n plus 1 minus 1, so is n plus 2, no, n plus 3, 1 to n plus 1, 2, 3. So, this many grid points, and also the equations we have is this. Now, one can solve this for, so what we can do is that by using these equations, boundary conditions, what we can do is we can write the y minus 1 in terms of y 0 y 1, similarly y n plus 1 in terms of y 0 y 1, and so solve the discretized equation one for I equal to 0, 1 to n, and replace y minus 1 and y n plus 1 by using the boundary conditions BCs. So, by using the boundary conditions, we replace the y minus 1 and y n plus 1. So, the resulting system of equations will be involving n plus 1 unknowns and n plus 1 equations. So, that is a compact, but the solving, this is one can get a, again we can get a tridiagonal, because y minus 1 is, see this is we are replacing y 0. So, y minus 1 we are replacing by what we can write is gamma 1 minus alpha 1 y 0, and so this is minus y minus 1. So, this is minus into 2h. So, this is minus alpha 2 y 1 into 2h. Now, when I write the discretized equation for I equal to 0, so we have a y minus 1 appears. So, I equal to 0, the first points, so that involves y minus 1, y0 and y1. So, once I replace y minus 1 by y0 y1, so again it will replace by it will involve y0 y1, and remaining I equal to 1, that involves y0 y1 I equal to 1. If I replace that is I minus 1 y0 y1 y2. So, that is a tridiagonal. So, similarly I equal to n, if I equation I equal to n grid points, we have y n minus 1 y n plus 1. Now, if I replace y n plus 1 in terms of y n and y n minus 1, so again it will be reduced to y n. So, that means a tridiagonal system results. Of order n cross n, not n minus 1. But however, this is a we can work out with that, but if it is a nonlinear equation, then this is not a proper way to solve because of instability that may arise because of this fictitious point. We are considering the grid beyond the domain. So, that creates a that may impose a instability for nonlinear situations. So, that is why we have to look for some other way to handle the derivative boundary conditions, which we will talk in the next lecture. Okay, thank you.